In this video, we're going to prove that polynomial and rational functions are continuous on their entire domains. So we're going to get this started with a reminder of the definition of continuity that we derived in the previous video. So there it is. A function f of x is continuous at the point a if the limit as x goes to a of f of x is equal to f of a. And we discovered in that previous video that this simple definition prevents all sorts of possible discontinuities from occurring, including infinite discontinuities, jump discontinuities, and removable discontinuities. So it's a really clever definition. Okay, so first we're going to prove that polynomial functions are continuous. And the first thing we need here is like a general definition of a polynomial. Remember that polynomials are just linear combinations of powers of x. So a general polynomial of degree n, and we'll call that guy p of x, could be written this way. I have a constant term, I'm going to call that c0. I have a linear term, c1x, and we're going to continue this way all the way up to the nth degree. So there's a general nth degree polynomial. Now we want to apply our definition of continuity at a point. So we're going to take the limit as x goes to a of this polynomial function, and we're going to attempt to show that that's equal to p evaluated at x equals a. So I suppose we should say this, that a belongs to the set of real numbers. It's just some arbitrary real number. And then we start evaluating this limit. So the limit as x goes to a of p of x is the limit of this huge expression, the statement of a general polynomial. So I have a c0 plus c1x. I'm going to skip the quadratic term just to keep it a little shorter, but we know we're following the pattern here, and we go all the way up to cn x to the nth power. Now we invoke our limit laws. So we know the limit of a linear combination of terms is just equal to the linear combination of the limits. And I'll post a link to the video where I first discussed the limit laws. Now we have options on the first term. We could just write it as the limit of c0, or we could write it as c0 times the limit of 1. It's the same thing either way. But the pattern is a little more consistent if we just write it like this. So I'm going to write it as c0 limit as x goes to a of 1. Here we're trying to express this linear combination of limits. So the second term is c1 limit as x goes to a of x. And we follow the pattern all the way to the nth term where I have a cn limit as x goes to a of x to the n. Now those first two limits, the limit of 1 is a limit of a constant. That was one of our basic limit laws, and that's just 1. And then the limit of x as x goes to a, that's just a. The one term that I'm showing here that requires a little bit of extra work is the limit as x goes to a of x to the n. We have to use our limit law that a limit of something raised to a power is the limit of that thing then raised to the power. So we'll just keep these other guys as limits for now, and then we'll wrap everything up in one final step. And what I'm saying about this final application of a limit law is I have a limit of something raised to the nth power that is equivalent to the limit of that thing, the limit of x as x goes to a, then raised to the nth power. Now we invoke our first two limit laws. The limit of a constant is just equal to that constant, so I have c0. The limit of x as x goes to a is just a, so I end up with a c1a for the second term. The next term is going to be a c2a squared, and so on and so on, and then we finish with a cn times a to the n. And then we realize this is nothing more than our original polynomial function evaluated at x equals a, so this thing is equal to p of a. And that concludes the proof because we were trying to show that the limit as x goes to a of p of x is equal to p of a. That guarantees this function is continuous at x equals a, and because a was just some arbitrary real number, we've shown that polynomial functions are continuous on the entire set of real numbers. So this is how mathematicians celebrate. We write QED at the end, meaning that which was to be demonstrated, and we're done. Next, we want to show that rational functions are continuous on their entire domain. So of course, there are going to be domain issues here because rational functions, those are fractions made out of polynomials. If the polynomial in the denominator happens to be 0 for some value of x, that has to be thrown out of the domain. So we're not considering those values. We're just saying it's continuous at every other value of x. And we need a name for this thing. I suppose we'll call it R for rational. So I'm going to say let R of x be a rational function. How do I write that? I can write it as a quotient of two polynomials. So I say let R of x equal P of x over Q of x, where P of x and Q of x are polynomial functions. And then again, our goal here is to apply the definition of continuity. So I want to take the limit as x goes to a, where a is just some arbitrary real number, of this function R of x. So again, I suppose I should say, let a belong to the set of real numbers. Now we start evaluating our limit. The limit as x goes to a of R of x. That's just the limit as x goes to a of P of x over Q of x. But then we use our limit law. The limit of a quotient is the quotient of the limits. So this can be shown as the limit as x goes to a of P of x divided by the limit as x goes to a of Q of x. But remember, we just showed that polynomial functions are continuous, which means the limit as x goes to a of P of x must be equal to P of a, and similar for Q of x. And then we have to make a side note here that Q of a is not allowed to be 0. So we'll put that in at the end. But first, I want to point out that P of a divided by Q of a is nothing more than R of x evaluated at x equals a. So this is equal to R of a, which essentially completes the proof. But we need to put in this point that there are some real numbers that are not in the domain of this rational function at all. And those are the numbers for which Q of a is equal to 0. So we've shown that this rational function is continuous for a lot of different points, just not the ones where Q of a is equal to 0. Those are the exact same points that were not in the domain of the rational function to begin with. And so we're done proving that rational functions are continuous on their entire domain. Again, we'll throw a low-key celebration by saying QED, and we're done. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.